Welcome to Chapter 5, Math 170. We are looking at 5.1 areas between curves. But before we get started, I want to kind of go over a few concepts, also known as preliminary work, so that if you take a little time to understand these ideas that we go over, perhaps the next few examples will be a little more clear for you. So let's look at a random curve F. And let's consider a point on the curve. I'll call it P. And you know, points always are named based on their X and Y coordinates, so I'll keep that there. And as you know from your graphing experience, whenever we talked about the X coordinate or the Y coordinate, remember, the X coordinate was the distance between the point P and the y-axis. So you can kind of see if you inspect that yellow highlighted length is X. Now, similarly, if you want to look at the y value on this point, y, as you know, is the distance between P and the x-axis. So if you could kind of refocus again and just kind of look at what's my horizontal distance, that's X, what's my vertical distance, that's Y. So that should kind of get us started. So now let's talk about two different concepts. So let's look at a curve F and another curve G. Well, I want to make it a little prettier, sorry. That was a little too freehand for us. Let me make it a little smoother for you. There we go. And what I want to look at are 2 points on these curves. So I have my point on the F. I guess it doesn't matter where I draw it, but I'll draw them over to the right a little bit. And I'll have my point on G as well. And I'll put it right beneath it just so that we can kind of see. And so if we connect these ideas, just kind of make sure these points, we talk about the vertical distance between the 2 points. Let's keep in mind that when we name these points, they both appear, if you are kind of re-looking at what the x-axis is doing, they both appear to have the same x value. So if you want to name the points, x comma something, the other one, x comma something else. So they both have the same x value. What is different is the 2 y values. One of them's higher than the other. So the point on F, I'll just call that y2. And the point on G, I'll call that y1, just to signify that they're different values. So now if we were to draw a rectangle based off of this length, and I'll call this length L, just because it makes it more sense to us. So if we were to take this length and just kind of create a rectangle, maybe a mini rectangle. And I should probably keep the same length like I said I was going to do. There we go. So suppose you want to talk about the area of this rectangle. And so you guys already know, okay, rectangles, areas are length times width. And if we're kind of looking at our length, we can now speak about it in terms of the differences of the y coordinates. So L, if I can mark this as well, so same idea. If you want to find the length, that is y2 minus y1. We've done this before with trying to figure out distances. Started off with delta epsilons. I think we had that same concept. Okay, now width is going to depend on how wide we make the rectangle. So if I can, I'll mark off. Looks like we have another x value. But we're going to refer to the width as delta x. So the change in x. So instead of calling it w, it's the y2 minus y1 times delta x, whatever that distance happens to be. So just kind of the moral of the story, just kind of noticing your x values are the same, your y values differ. And we're kind of looking at creating area of a rectangle with using y values and delta x. So guess what we're going to do this time? Maybe you don't have a guess yet, but I'll tell you. I'm going to give you functions orientated a little bit differently. Let's draw f over here, and then maybe we'll draw g over here. So maybe if I want to be precise, I should probably make it look like a function. Here we go. Something like this. Okay, so now we're going to do the same idea. And we're going to call a point on the function g. And then we're going to have the same height, a point on the function f. And just kind of keep in mind, we're going to create a rectangle off of this point. So if we were to name their ordered pairs, just kind of looking at the x values and y values, you might want to just kind of take a time to pause and say, well, which values are the same? Are the x values the same or are the y values the same? And you kind of look at it and say, wait a second, looks like, to me, our y values are going to be the same because they have the same height, distance from the point to the x-axis. So now here what's changing is we've got two different x values. So if the x values are different, just kind of mark them as such. You can name them with it whatever subscript you'd like. I'm going to go with x1 on the g and x2 on the f. So now let's talk about drawing this rectangle based off of this length right here. So I'll kind of draw this rectangle. This time it's orientated horizontally. So if you want to specify what is our length, just like we did earlier, we're going to have to realize that the length would be the difference of the x's. So another way to write it, absolute value if you want, but we would also say that's x2 minus x1 if you have the larger point minus the smaller point. So again, if we're looking at the area of this rectangle, we kind of start off again, area is length times width. In our case, the length this time is designated by the difference of the x's. And now you're probably guessing, well, what is the width going to be talking about? Well, if we do look at the width, it is based on your y values and how far apart you would make that rectangle the width. We call this delta y. So what you want to kind of pay attention to, if I can try to promote this a little bit faster, it kind of depends on what axis you're slicing up. So for instance, when I made vertical rectangles on the left, I made a single rectangle and it was slicing up the x-axis. That was using what delta x was. If I was looking at the figure on the right, this is the y-axis that's being sliced up. So this is where we're getting the delta y from. So having said that, two specific formulas to help us find areas between two curves. And geometrically, I always encourage you to sketch them because it's going to make more sense with the formula. So I'll start off. We're going to start off with kind of the figure on the left again, or some version of it. We're going to have our function f, and then we'll have a function g. If I can get that to draw, there we go. And a lot of times you're interested in figuring out what the area is between the two curves. And what happens is you have to care about, well, how far do you take the area? Well, they're always going to tell you, start at some value A, or x value A in this case, and end at some x value B. Well, in order to understand how this is going to work, what they have to do first is they actually have to find the area underneath F completely. So I can draw that and then I'll kind of show you what we're looking at. So the area under F would be designated somewhat by the yellow highlighted area. So notice that area is larger. But once you figure out what the area under F is, if you can then subtract out the area under G, which I'll try to color and now it looks orange, you will then have the area that you really wanted. So basically you're saying, you know, bigger area minus the smaller area, you're cutting it off, and that's how we're getting the differences of the two functions. So I would say, if I'm really trying to interpret this, I'm going to have to say, well, let's always remember this. If you're trying to find the area between two curves and they're situated so that we have a curve on top and a curve on the bottom, the curve that you always write first is the one you see on top. The curve that you always write second is the curve that you see on the bottom. And then if you can get that, then you're good to go. Now notice what we're taking the integral with respect to as well. This is dx, mainly because when you are integrating, you'd be slicing up the x-axis into different pieces. So if the x-axis is getting sliced up, you're taking the integral with respect to x. Now on the other side, what happens if you're kind of looking at the curves from side to side? So I'll say, I think I'll do something, I'll draw G, kind of like what we did in the last picture. So we have our G curve, and let's draw our F curve. And again, if we're looking at the area between the two curves, we have to kind of think about this a little bit differently. So I'll designate this. This is our wanted area. So this time, instead of slicing up the x-axis, we'd have to kind of understand that we're, in a sense, slicing up the y-axis. And so the idea, again, if you are to try to find the area between the two curves, you would first have to find the area to the right of your rightmost curve, I should say. So that would be considered your f of y. And then what happens is you would have to subtract off the area to the right of your, I guess this would be the leftmost curve. So once you slice that area off, or you cut it off, you're going to have the area of the intended region. So again, if you could always remember, whenever we're trying to look at the axis a little differently, notice that you're slicing up the y-axis into different pieces, hence the name dy, what you're taking it with respect to. And if you could remember, kind of like, so we don't have to deal with absolute values, we're basically saying it's always the bigger curve minus the smaller curve, or in this case, the right curve, the curve on the right, subtract off the curve on the left. If you can remember this, you're always going to have the areas quite nicely, but it does matter how you're slicing the axis. That's going to depend on whether you want the function in terms of x or the function in terms of y. Now, I have a feeling, since you've been working with x all this time, you probably are more comfortable when you slice up the x-axis. But this is why we always said you have to write that dx at the end of your integral, because it does matter with how you integrate. So we're going to look at a few examples just to kind of see, get the swing of things. We're going to look at example 1. It wants us to find the area bounded by the curves f of x equals x squared minus 4x and g of x equals 2x. Now, you want to be careful. They name f and g just because they try to talk about them as different curves. And I know our formulas always start off with f and g, but it always depends on how the curves are orientated. So remember that your f curve is always going to be the one that's on the top or to the right. So kind of be careful with that. So what you want to do anytime you're going through these, I encourage you to try to sketch a fairly accurate curve, and you want to always indicate where your points of intersection are. So you can use your TI to assist you if you feel that you'd like to, and that might be a good idea. So let's see if we can pull that up. And I know we could probably do this without the TI, but might as well utilize the technology. So let me see if I can type in f of x. So that's x squared. I know it's a parabola, x squared minus 4x. And then we'll also type in the g of x, which is 2x. It's nice, everyone's in terms of x. I assume we have a standard viewing window. We do. Okay. So what's important to understand and see when you have your sketch is you want to see the points of intersection. So it looks to me like the points of intersection, one of them, they're intersecting at the origin, and it appears I have to see a little bit higher to see where the other point of intersection is. So I'll adjust my window a bit. It looks like it's relatively close to the y max, so maybe I'll go with like 15 or 20, just so that I can see the full idea. Okay. So keep in mind our f function is blue and our g function is red. So that's going to give us a good idea. I'll show you analytically how to calculate the points of intersection in a second, but you could also, if you have the curves and you're taking time to draw them on the TI, it doesn't hurt. You could also calculate the intersection. I'll do the other one, because I have a feeling the other one's at 0, 0, but we'll see. Oh, it's a little slow today. Let me go this way. It's a little faster. Yes, the TI is tired like us. Don't worry, we're almost there. We're almost through the class. So see, when I calculate the intersection, first curve, second curve, make it guess, and it finds out that the intersection is at 6, 12. So we'll go back and we'll say like, yeah, we can use the TI to find these points. They'll be very important in terms of the limits of integration. But it kind of matters, like which one are we going to use? So let's go back. Sketch our findings. So the way I see it, I'm kind of understanding, I want to make sure that my f, I know it looks like it went through the origin. We got ourselves a parabola. So fairly accurate. I'm going to label it just to make sure I know what I'm dealing with. And then we also had a G. And it looks like it went through the origin. It was a line. And we could have drawn this by hand, I know. So what we might be interested in, like I said earlier, are our points of intersection. Let's look at that. We already figured it out as 612. I'm pretty sure that we're at 0, 0. But just in case your professor takes your calculator away from you, happens sometime. If you're going to play with the points of intersection and we want to talk about it analytically, the points of intersection occur when your f of x values are equal to your g of x values. So we see there's 2 places, but we could actually solve mini equation this way. I have x squared minus 4x equals 2x. Looks like we've got a quadratic equation. We could subtract 2x from both sides. I have x squared minus 6x. And then we notice that we have x times x minus 6 equals 0. So we're going to have x equals 0 or x equals 6. And so if you guys can see, we see 0 and we see 6 going from there. So whether you use the TI, whether you show it by hand, just make sure you can utilize both if you ever need to. Now, if you need to find the y coordinates, you may want to wait. It kind of depends, like we'll only need to find the y coordinates if we have to slice it up where we slice up the y-axis. So let's interpret before we try to go further. We've got 2 choices here, or 2 options. We can talk about the top minus the bottom curve, or we could talk about the right curve minus the left curve. And so if I kind of play around with this, I have a feeling, I can clearly see that there's a top curve and a bottom curve. To me, it looks like the G curve is going to be the curve on top. So if I were to draw a mini rectangle somewhere along the curves, the 2 curves, I definitely can see that G, the red curve, is on top. And F, the red curve is on the bottom, the blue curve is on the bottom. This is why I like to color code. So it appears, if I were to make a number of rectangles, remember the idea of finding integrals, by the way, it was to make a bunch of rectangles, and the smaller you slice them up, the more you get closer to the actual area of the oddly shaped region. So I have a feeling that this is going to be the one that we like. It's probably our best choice. And we like integrating with respect to x. That's something we're used to. But I also want to just explore if we were to try to slice it the other way. So let's check out, let's look at this side. If you were going to decide that f was on the right and g was on the left, you can draw a bunch of rectangles and it would work out most of the time. But what's happening and what would cause me not to pick this? At one point after I'm drawing all my little rectangles, and it's really good test, we're good so far. But somewhere around here, notice when I draw my rectangle at the bottom, and maybe I'll highlight that for now. At some point, we end up touching the same curve, and that will lead us to not wanting to use this option. We'd have to split it up into 2 different regions, and we can, but I don't think it's going to be useful to us. So this one kind of leads me in a sense to a dead end. No, I say. And the reason why is I'll hit the same curve. At some point with our horizontal rectangles. So this one's out of the mix for now. So just kind of do that test for yourself, draw kind of some mini sketches, and then see how this works. So let's erase kind of what we had earlier. Well, I don't want to erase the curve. I like that. There we go. I'll have to be a little bit smaller here. I'll do the best I can. I just want to clean up the picture so it's nice for us to see. Okay, so you guys get the point. We can redraw if we need to. Oh, well, not with an eraser. There we go. I'll redraw with my curve just a little bit, make this picture back to the pretty picture that we spent so much time on. All right, my friends. So let's see. Again, I wanted to slice it up vertically. And so if I draw a sample slice, I should say, that's going to help us see the top, bottom, and what our delta x would be, or the reason why. So I always kind of recommend sketch a sample rectangle to help you see who's the top, bottom, and delta x. So that would be kind of indicated if you're ever going to show work on an exam. This kind of justifies why we're taking the integral with respect to x. So having said that, if we're taking our chosen option, when you go to start to look at your points of intersection again, if you're going to slice up the x-axis, you already have your starting and ending points for your x's. So here, little note, we don't need the y coordinates. Since you're integrating with respect to x. So see how it kind of makes a little bit of sense to just really, I mean, you're going to have to find points of intersection anyways, but before you spend too much time and get involved in all the algebra behind everything, just look at how you're going to integrate with respect to. Are we going to make vertical rectangles or are we going to make horizontal? And we decided it was going to be the top minus bottom. So now, having said that, we can now look at our area formula. In integral from a to b of your two functions being subtracted with respect to x. And remember, the formula itself is just specifying who's on the top and who's on the bottom. So I'd like to just really give you an idea that we have our top function and then our bottom function. And so the way they're named according to what we're looking at, it appears that it was g of x that was on top and f of x that was on the bottom. So be careful. The formula that you see is just an idea, and it really depends on the orientation. So now that you kind of have that down, you then have to kind of fill in, well, if we're going to integrate, we should probably know who our limits of integration are. And you can see why we took a little bit of time. Again, if we're slicing up the x-axis, we're going to go from 0 to 6. And so we already have those nice x values from our previous work. And I like that. We have a 0 at the lower limit. That's good to know. Now, all you have to do at this point, if everything's already in terms of x, just replace g of x with its formula. So in our case, g of x was 2x. We had a minus sign from the formula. And f of x was more than one term, which is x squared minus 4x. So don't forget to include it in parentheses because distributing will matter. So now we have our formula, our integral. And so just for a little practice from the last sections, just, we might as well take time. We're going to integrate from 0 to 6. What do? It looks like we have polynomial in the integrand. Take some time. Maybe we can distribute. So we have 2x minus x squared plus 4x with respect to x. That's why it's really important to write that. And before you try to integrate by hand, it's always nice if you want to combine some like terms. So I think I have 6x minus x squared with respect to x. And then now's the fun part. Let's integrate. If we integrate, we should have 6x squared over 2 minus x cubed over 3, but everything would be evaluated from 0 to 6. Got to remember that fundamental theorem of calculus. So if you prefer to clean it up, let's do so. I think I have 3x squared minus x cubed over 3, or I can say 1/3 x cubed. Still evaluated from 0 to 6. So this tells me I can take the 6 and plug it in. And so that piece would subtract off whatever I plug in with the 0. But if there's x's in both of those terms, you're pretty much subtracting off 0. So we take a little bit of time. 3 times 6 squared? Oh, so 6 squared first, 36. Get your calculator out. You got to use your brain for more important things. So I have 6 squared, 36 times 3. So that's going to give me 108. And then 6 cubed divided by 3. So 6 cubed. To me, that's 216 over 3. Maybe that's a nicer number. It is. So that should give us, I'll go sideways, 108 minus 72, or 108 minus 72 is 36. Now, what you need to remember how like we find integrals and we were cool, we just put the number down. But remember, the problem's asking us to find the area. So what we have to do is don't forget to include the units. So we need this, very important. And the reason why it's important, because the problem asked for area. It didn't say find the integral. Okay, let that sink in. So nice application. As long as you have a good idea of what the pictures are doing, then you probably be able to get through this section quite nicely. I want to show you a few more examples just to make sure we catch everything. So let's take a look at example 2. This time we're going to find the area bounded by the curves. X equals y squared minus 4y, and x equals 2y minus y squared. So the minute I see this, everything is in terms of y. I have to kind of keep in mind, I have a function of y in both cases. So should I say functions of y plural? So that's something to kind of say, okay. And sometimes that might be a good hint to us, like, maybe they're trying to promote something. Like where do we take the integral with respect to? But before I truly decide, I really need to see the picture. So I'm interested in seeing the picture of the graphs. And I have to think back to what's going on with conic sections. I think I have some parabolas going on. I think there's some horizontal parabolas from here. So I have a feeling. I have horizontal parabolas, aha. So horizontal parabolas. And you can kind of tell what they are. The first one, it looks like the y square is positive. So right away, I kind of know, like, okay, that guy's going to open up to the right. And the second one, the y squared is negative, so it's going to open up to the left. Now, what you might want to do, it might be to your benefit if you're having a hard time of trying to understand, like, do you want to solve it for y and type it into your TI just to give you a better idea? That's okay. I'm going to find a few important points on the curve and see if we can interpret this our own way, and then we'll go from there. So what I kind of want to do, if you'd like to, you can name one of them F and G if that's something that you'd like. Let's see. I'll wait, because maybe you care. Do you want to name the first one F? Let's see. So F of y is y squared minus 4y. We'll call it that way. And G of y is 2y minus y squared. So if we kind of have that going our way, let's figure out what our y-intercept is. Try with the first part. Okay, so remember, when you have a y-intercept, we can set the f of y equal to 0 and figure out who our y values are. So that might be a quick way to do that. So you have y times y minus 4 still equals 0. And so that would give us y equals 0. Oh, cool. Our y equals 4. So let's plot that. If I plot, I should probably make some nice coordinates. Y equals 0, y equals 4. 1, 2, 3, 4. Let's have one here. 1, 2, 3, 4. There we go. So that's good news. Now I know we're opening up to the right, so I have a feeling my vertex is going to be to the left of the origin. You want to find it there, or might as well. Let's look at that. So I have a formula for vertex. If I have it in ax squared plus bx plus c form, the vertex is negative b over 2a. But because we're in terms of y, it's telling us that y equals negative b over 2a. So in our case, if we were playing with this, if I can kind of notate, my a is 1 and my b is 4. So let's kind of plug that in. And let's keep the sign of the 4. Let's do this. Okay, so negative, that's coming from the formula. The b is negative 4. Formula all over 2. And this time the a is 1. See, it's the coefficient of the squared term and the linear term. I'll take a little time, simplify that a little bit more. What do we have? 4 over 2, which gives us 2. So now we have the y value of the vertex. So we kind of know personally it's somewhere along here. That's good to know. And we just want to find the x value. So the x value is the function evaluated at 2, which is 2 squared minus 4 times 2, which we have, what, 4 minus 8, or negative 4. And now we have our vertex. Vertex is going to be negative 4 comma 2. Only the x value goes first, the y value goes second. So let's plot that. 1, 2, 3, 4, positive 2. There's our vertex. And that's pretty good to go. You have a pretty accurate function there. If you then want to kind of pick other values, kind of some patterns of parabola, we'll have some nice intermediate points right here if that's something you're interested in. But I feel pretty confident that I've got a pretty good parabola that I can then draw for myself. Okay, and yeah, we open up to the right. And if you're not confident about this, just keep picking values of y to plug in and find corresponding x values, and you'll find something for you. So we'll call this guy f, because we already did. based on our notation. And we could do the same thing for G. What happens? You want to find your y-intercept? Go for it. So just kind of the same thing. If you want to find your y-intercept, it's the value where x is 0, or g of y is 0. So we do a little bit of math. Looks like we can factor out a y to get 2 minus y. So that's going to leave us with y equals 0, or 2 minus y equals 0, which gives us y equals 2, moving that y over. So that's kind of nice. I have 2 y-intercepts. So at the y-axis, at 0, I see that, and at 2. Now it's a good time to find the vertex. If I want to find the vertex for this one, I still go the same manner. Y is negative b over 2a. So in our case, who is b? In our case, b is 2. And a this time is negative 1. So what happens here is we end up having, 2 over 2, negative 2 over negative 2, positive 1. All right, cool. Got that y value of the vertex. Now, if you want to find the x value of the vertex, same story. X is equal to the function evaluated at, oh, shouldn't it be f? I think we called that g. So we have g of 1. So that's 2 times 1 minus 1 squared. Or we have 2 minus 1, which is a 1. Oh, so our x value and y value of the vertex end up being the same, 1 comma 1. And so what we end up having, you want to plot it for yourself. And it looks like we have a good idea of what our vertex is doing. If we're interested, just to make this clearer, I have a feeling our function is going to do something like this. Maybe not be so pointy. Let's see. So now we've got, let's see what we got. We have our points of intersection. I want to figure out, I kind of see 0, 0s, probably a good candidate, and I just maybe want to see what would that accuracy be, maybe for that one. So let's take some time, figure out our points of intersection. And that happens when your two functions are equal. F of y equals g of y. So we can kind of set them equal to each other. Y squared minus 4y equals 2y minus y squared. And I thought the y squares would cancel out, but no, remember when you move everything to one side, sometimes we make assumptions and we have to be careful. We actually end up getting 2y squared minus 6y equals 0. That's a nice quadratic equation to solve. We could factor out the 2 y's. So that's going to leave us with 2y times y minus 3 equals 0. So that gives us y equals 0 or y equals 3. Now, if you're interested in finding the x values, sometimes you can visualize it. Oh, well, the intersection is at y equals 3. I'm good there. I know I should have drawn that red part a little nicer. I might be able to figure that x value out by inspection. But if you really want to be accurate, we're going to need to make sure, do we want to find those x values? So let's wait. I do have the points of intersection. I'm feeling pretty good right now. Before I try to care about what the x values are at that point of intersection, I might want to decide which way I'd like to slice my function. So again, we have choices. Now is finally time for the area, huh? Okay. So our choices, we could either say top minus bottom, so options. So top curve minus bottom curve. Now, if we do that, you can make a bunch of slices and see what happens. We do pretty well while we're in the middle because we do see that clearly the top is the red, the bottom is the blue. But the minute you kind of go towards the vertex, you end up slicing the same curve twice in both cases. So this would not be, that would not be a good option. It's not going to help us. We'd have to split up the integration too much. And actually, let me just undo everything. So that's not going to work. Nope. So what's our only option left? Right minus left. Okay, so let's just double check before we can clearly do this. If we go right minus left, that would mean we're slicing up the y-axis. So our rectangles, when we draw them, we'd have to have a clear right side and left side. And in all cases throughout that entire region, you only hit the curve once at each time. So this is going to give us a good idea. Let's draw our sample rectangle. I'll kind of put it right in the middle, or somewhat of a sample rectangle, sample slice, I should say. So that tells us we care about delta y. And it also gives us an indication of who is on the right and who is on the left. If you want to be a little more clearer, in our case, the right curve was our g of x, and our left curve is our f of x, based on our rectangle that we drew. So now that kind of sets us up for our integral. So we can set up the area. The area is integral from a to b. And this time it's right minus left. So this time it's what? G of y minus f of y dy. And then this kind of makes us happy because, okay, we don't have to worry about the x values for the points of intersection. So now the only thing you have to do is put numbers in for these. So we should have what? A and b are y values. So let's look again at our y values. The points of intersection at y equals 0 to y equals 3. So that's our dy. That's the region of the y-axis we're taking, which makes up the particular region we were concerned with. So we should have from y equals 0 to y equals 3. And they're just understanding who's g of y. That's 2y. Let's draw brackets. 2y minus y squared. And then we're going to subtract off f of y. And that's y squared minus 4y with respect to y. So what happens now, it's just a bunch of algebra and integration. So let's simplify the inside. I've got 2y minus y squared, but I'm going to distribute that negative sign. So minus y squared plus 4y. Take time. So we go from 0 to 3. So let's combine like terms. So negative y squared minus y squared. So we should have negative 2y squared. And 2y plus 4y is 6y. Kind of similar to the last one in a way. It looks like we have simplified the integrand as much as possible. So now it's time to integrate. So if we're going to integrate, we should get negative 2y cubed over 3 plus 6y squared over 2, all evaluated from 0 to 3. And so we can clean it up just a little bit. Negative 2y cubed over 3 plus 3y squared, still evaluated from 0 to 3. Now we're lucky that lower limit's 0, so all we have to worry about is plugging in that 3 to our function, because you would end up subtracting off 0 anyways. So take a little time. What do we have? 3 cubed over 3 is 3 squared. And so we have what? 2 times 3 squared, that's negative 18. And 3 times 3 squared is 27. So negative 18 plus 27. And so that's going to give us 9. And don't forget, get all happy when you find your answer. Don't forget they asked for the area. So what do you have to write? Not just a 9, but a 9 square units. And that will help us out. That's kind of a nice problem. Sometimes the way you do see the functions kind of tell you and give you a heads up of what variable you're going to integrate with respect to. But I really, really want to encourage you, draw the picture, draw sample rectangles, just so that you can verify for yourself. So we had an example of slicing up the x-axis when we took the integration with respect to x. Example 2, slicing up the y-axis when we took the integration with respect to y. Let's play around. Let's give you one more that sometimes tends to throw us off. Example 3. They want us to find the area bounded by the curves. Oh, there's those trig functions again. F of x equals sine x, g of x equals cosine x equals 0, and x equals pi. So you might want to use a TI to help you. It could kind of give you an idea, gives you an idea with your x min and x max. That might be a good starting point. I'm going to attempt to do this by hand. Because I have a feeling if they already gave us x equals 0 and x equals pi, I'll make it larger. That's going to help us out. So, by the way, those curves, if you are drawing them, x equals 0 and x equals pi, those are vertical lines, the best we can draw them. So that might not be particularly interesting in our integration, but we have to see what happens with the rest of the functions. So if you remember, f of x equals sine x, if you want to take some time, just kind of a quick idea. If you have sine x, it starts at 0, it ends at 2 pi, it's 0 in the middle. We have a high point and a low point. So it looks like with the sine, we're going to 0 to pi. It looks like we're going to have like an upper half of a, somewhat looks like a parabola in a sense, maybe a half circle, sort of. So we know it, sine starts at 0 and at 0 at pi, and it should be 1 at pi over 2. Okay, so let's draw that the best we can. Probably should be a slightly curvier, but we'll see. Okay, so that's our f, according to what our pictures are. Okay, I'll draw that there, I'll label that. Now, if you remember g of x, let's draw that. Y equals cosine x. If you remember, it starts at positive 1 and it ends at positive 1 at 2 pi. In the middle, it's at negative 1 at pi. And it crosses pi over 2 and 3 pi over 2. So again, if we're looking from 0 to pi, we're going to start off at 1. in the middle with pi over 2 will probably cross through there, and then -1 is where we'll end. You know, it looks like a line, but it should be a little curvier, so kind of be careful there. Feel free, let's verify on our TI. And then what I want to kind of have you guys notice is, again, it's the area bounded by the curves. So if you really look at this, what I'm noticing, I'm bounded by the curves. It looks like there's a somewhat of a triangular region, sort of curvy. There's one of the areas. And then we have another region. I don't even know what shape I can describe it as, but it's kind of like wavy. Maybe it kind of looks like a bird facing sideways, or at least part of a bird facing sideways. I don't know. But here, when you look at this region, again, what we're talking about, bounded by all of the curves that they mentioned, x equals pi, x equals 0, and the two y equals cosine and y equals sine. So what you would probably notice right away is that you have two regions. And so if you have two regions, most likely you're going to need two integrals, because they're not nice regions either. So if we have two regions, we are going to need two integrals. And that has to go with kind of calling it, you know, area 1 and area 2. And we've done this before. Total area is the sum of the two areas. And so that's fine. We can do that. What we might be interested in is understanding who's the top function, bottom function, or left function and right function. Let's see. What can we do for ourselves? So let's see if we slice. If you're interested, maybe you just go with the one you're more comfortable with. Personally, I'm comfortable with making vertical rectangles. So if I make vertical rectangles in A1, I'm only hitting each curve once. So I feel pretty good. I can do the whole top minus bottom for A1. So I'll go with it. I'll put the limits in a second, but to me it looks like my top curve is G and my bottom curve is F. And it looks like I'd be integrating with respect to X because I'm making those vertical rectangles. Now we might be interested, we do know the X value that we're starting with. We do know that that X value is 0. But I have to figure out where I'm stopping. So let's kind of look at that a little bit more clearly. I'm not stopping at pi over 2 because that would include some empty space. I need one more bit of information to complete this integral. And it happens to be this point right here, whatever this X value is. And by inspection, or maybe by using your TI, you're going to find a decimal one, but we kind of have to think harder about this. We really want to find the exact value because you can't just approximate the limits of integration. So remember, the points of intersection, and actually there's only one point of intersection. That is when your f of x equals to your g of x. And our f of x in our case was sine x, and our g of x was cosine x. And now with a little bit of trig, you're saying, well, when is the sine equal to cosine? Or if you're realizing that particular point, you're never going to have cosine x equal 0. If we're beyond 0 already, a couple of things you could do. You can play around with dividing by cosine x. So you kind of ask yourself, oh, what is sine x over cosine x? That's where tangent x equals 1. So that might also give you a heads up. With tangent x is equal to 1, that's happening at pi over 4. Or if you didn't think about it that way, sine and cosine x are equal. Sine of pi over 4 is square root of 2 over 2. Cosine of pi over 4 is square root of 2 over 2, and that's kind of indicating that's why we're taking that point of intersection. So my friends, that is the upper limit for that first region. So that also gives us the lower limit. Let's attach on that second area. Let's interpret. We're going to go from, let's just kind of verify one more time. As we're slicing, do we still feel confident that whenever we make our slices, if we're making vertical rectangles, we're only hitting the curve, each curve one time? So that is good. We can still take everything with respect to x. So I'm interested in taking the region from pi over 4 until pi. So that's our limits of integration, pi over 4 to pi. And then just kind of, if we are going through this, let's be clear. We're taking with respect to x, that's fine. In this case, our top function is f, or area 2. Subtract off our bottom function, which is g. So as long as you have that set up, you're in good shape, just so that you understand who's the top, who's the bottom. Now let's just kind of simplify. Let's see if we can find numbers for these. So I have 0 to pi over 4. Now g, in our case, is cosine x. So I have cosine x minus sine x with respect to x, plus integral from pi over 4 to pi. My f is sine x, and I'm subtracting off cosine x with respect to x. So I'm replacing the functions with their actual formulas. And so now we know, okay, we got to integrate trig functions. Well, a little note on the side, anytime you're integrating trig functions, you're trying to figure out who was the function before you took the derivative. So I kind of do this whole f prime. So I see sines and cosines. So if I start off with f of x equals sine of x, the derivative of sine of x is cosine x. So if I see a cosine x, I know right away that the integral of cosine x is sine of x. And similarly, if I start off with cosine x, the derivative of cosine x is negative sine of x. So then I just have to be careful with signs, with the sign when I see that inside the integrand. So if I do this, let's go from here. The integral of cosine x is sine x. Now, if you take the integral, it's kind of like the integral of negative sine x, you can actually have cosine x back at hand. And so that part is evaluated from 0 to pi over 4. We're going to add this. The integral of sine x, this is where you have to be careful. The integral of sine x is, it's not there, but we have to say it's negative cosine x. So let's pull that out. Negative cosine x minus the integral of cosine x is sine x. So it's the signs, plus or minus, is going to determine issues for us all. So now we're integrating that with respect to x on pi over 4 to pi. Be careful, we can't just take any of these out. We're going to have to take a little time on this. So when we, whenever you have trig functions, you want to be careful. We can't assume that 0 will make anything disappear. So take your time when you're evaluating these. If you're going to now plug them in with the fundamental theorem of calculus, we have sine of pi over 4 plus cosine of pi over 4. That's the first part. Subtract off sine of 0 minus cosine of 0. That's that first piece. I have plus the second piece, area 2 or region 2. I have negative cosine pi minus sine pi. I'm going to subtract off negative cosine pi over 4 minus sine pi over 4. There we go. And now you just got to be really careful. And let's determine everything. Let's go and slowly walk our way through this. Sine of pi over 4. You guys remember the 45, 45, 90 triangle? Square root of 2 over 2, or 1 over square root of 2. So that's where we have this, square root of 2 over 2. If we rationalize. Cosine of pi over 4 is the same thing, so that's good. Square root of 2 over 2. So now we're subtracting off sine of 0. Now sine of 0 is 0. That's fine. And let me make sure. Plus sign, plus sign. There we go. See what happens. We're not taking care of the signs. That's why I always have to write out my original piece above. It helps me really see. Okay, so cosine 0. Cosine cosine of 0 is 1. So we'll attach that in. Now we go from here. Okay, so now we have negative cosine of pi. Cosine of pi is negative 1. Sine of pi is 0. And cosine of pi over 4, but there's a negative, so we have square root of 2 over 2. Same thing with sine of pi over 4, minus square root of 2 over 2. So we're just plugging in all these values. Let's clean it up a bit. So what do we have here? Square root of 2 over 2 plus square root of 2 over 2 is 2 square root of 2 over 2, which gives you square root of 2. We have a minus 1 plus minus a negative 1, so that's plus of 1. Now be careful here. We have minus, now negative square root of 2 over 2 minus square root of 2 over 2 is negative square root of 2. But minus a negative makes it a plus. So we have to be careful. So if we simplify, we are almost there. We have 2 square root of 2's hanging out. The ones neutralize. So we have the area of our figure, but because again, don't get too stuck on this, the area has to have the units. So don't forget to write square units because you are addressing the area, not just the answer to the integral. That's really interesting. A lot of pi's over 2's and all of that. So good exercise, not only in determining curves, but also helping integrate those trig functions. Once again, get used to that. Calc 2 is going to come your way. Okay, so let's see. You know, by now you've probably gotten used to integrating and you're probably a little bit tired when it comes to some of the polynomials. So some of the questions, you might have some freedom to pull up your TI. So let's see if we can do that. Okay, so example 4, this would be kind of similar. If we try to have you apply something to like a quiz or a test, sometimes we're really just interested in seeing you guys set up the integrals, and then whether or not you can integrate, we've already tested you on that. So might as well let you use your TI. So let's see what we can do for these. So I want to set up an integral to represent the area bounded by the curves y equals 0, y equals square root of x plus 1, x equals square root of y, and y equals 1. So right away, if this is helpful, remember y equals 0 is the x-axis. And if I want to talk about y equals 1, I know that's a horizontal line. At least I can draw that part. So I know that the region is going to be bounded in between those two values. Now let's look at trying to graph the other ones. So y equals, see if I can graph that, y equals square root of x plus 1. I know that that's like y equals square root of x, but it's shifted to the left 1 unit. So I do know that it would start here. And the way the square root of x function goes is it kind of goes at 1 comma 1, and then I think we'd have to go to 4 to get a 2. 1, 2, 3, 4. We'd probably see it doing something like this, although we don't really care what happens outside. Okay. So I'll move that so I can label that for you all, just in case. There we go. So now we kind of narrowed it down a little bit nicer in between here and a little bit of curvy part right there. We want to look at the other one more time. This time it's called x equals square root of y. So whenever anything's solved in terms of, solve for x in terms of y, I might manipulate it again and say, okay, if x is equal to the square root of y, if I square both sides, I get x squared equals y, or y equals x squared. And it only helps when you're using part of it. So let's see, y equals x squared. We're going to have to be really careful. Maybe make an XY chart. It matters what the y values are, because if you end up having them be negative, you have imaginary root for that function. But we already kind of know y equals x squared. Kind of nice already. So you could play around. If you're looking at the table, it's already in terms of a nice perfect square. If you want to only choose perfect squares for the y values, then that's going to give you your x values. If you want to see what it kind of looks like in terms of y, then you also have an option there. So again, I have 0, 0, 1, 1, and I think we have like 2 comma 4 or something. So 1, 2, 3, 4, something like this. Yeah, it does look like the right side of a parabola. Okay, so let's kind of go over again. We're looking for the region that's bounded by these particular curves. So y equals 0, y equals square root of x plus 1, x equals square root of y, and y equals 1. So we have this region in here. Kind of looks like an eye, almond-like shape maybe. Not quite a rectangle, not quite a parallelogram. So we have an idea of what it looks like. So then you have some options. You kind of say, okay, we always start off with maybe what we're more familiar with, and we can say, can we slice it top minus bottom? So that means you're making slices like this. That means you have a dx. We're going to slice up the x-axis. And that is true. We can do that. That's actually kind of nice. So might as well. So what do we have? Our area. Here's where we have to be careful. We just have to figure out what x values we're starting and stopping at. And based on based on our graphs, you know, our key characteristic points actually were very clear to us. We don't have to do any intersections or anything like that. But it looks like we can go through most of it. So let's look at this a little more clearer. Okay, so I know I can go from -1. That's definitely my starting point. Let's talk about who's on the top. The top function is square root of x plus 1. That's fine. And the bottom function is y equals 0. Okay, so we're subtracting off 0 as our setup. Now the reason why I stopped there, when you go beyond 0, pay attention to who's on top at that point. After 0, the y equals 1 is on top. And then the x equals square root of y is on the bottom. So we couldn't just go straight from -1 to +1. So you have to be careful. So let's kind of clear that up. So again, we're taking this with respect to x. So that's the kind of the first region. The second region, this time around, we can start up at 0, go to 1, and then we're paying attention to who's on the top. In this case, it's going to be y equals 1. Subtract off who's on the bottom. This time it's the y equals x squared. So that's the x equals square root of y function, just in case. We had to manipulate it depending on who we're taking it with respect to. Okay, so we still have, with respect to x, and so that will cover our entire region. And so if you want to clean this up, you can. Like whenever you subtract off 0, that's fine. We have -1 to 0, square root of x plus 1 with respect to x, plus 0 to 1, 1 minus x squared with respect to x. So this is where the setup is coming from. At this point, I'd prefer to use the TI to help us find the answer. So let's see, let's pull that up. It actually, yeah, it asked us to do that. So yeah, might as well, I'll go with it. Okay, so remember when you use the TI, we're going to call up math, and then we're going to go to item number 9 under the math menu, function integral. And so I could enter in the first limit, or the first integral, -1 to 0. Okay. Now, the integrand is square root of x plus 1. With respect to x. Yes, okay. Add on. We can take care of this all in one shot if we wrote this down on our paper. Call up the integral again. Number 9. We're going to go from 0 to 1. And this time around, we're saying 1 minus x squared. Again, with respect to x. And so now we have our integration. Because we have definite integrals, our calculator will find it for us. And so we have about 1.333, so on, square units. So let's go back and record that. So with the TI, we got approximately 1.333, and don't forget square units because it asks for the area. So that's good to go. We could stop at that point, but I do want to point out that you could have also attacked this problem by using the other option. And so just to kind of go over that, just to confirm, we should be getting this. we should have right minus left. That's another option we could have done to attack this area. And if we do right minus left, remember, we're slicing up horizontally. So whenever you slice up horizontally, you're taking the integration with respect to y. And if you look at this a little more carefully now, when you slice horizontally, you don't have to use two different integrals because the same curve is always on the right and the same curve is always on the left. Also, what's neat is your limits of integration are already set as well. So in this case, if I was looking at this picture, my area on the y-axis would go from 0 to 1. And then my right curve, remember, if everything is in terms of y, the right curve is the orange curve, we would have to have it as square root of y. Let's color code that just in case. And then we'd subtract off. We're going to subtract off the green curve. Now, the green curve, let me kind of make sure. Oh, I just drew that purple. Sorry. The green curve is y equals square root of x plus 1. Okay? But you can't just call it y. You have to write it in terms of it being solved for x. Because remember, when you use the right minus left, x is a function of y. So it has to be solved for x. Okay, if we solve for x, past tense I should say, we're solving for x. Y equals square root of x plus 1. What do we do? Square both sides. So y squared equals x plus 1. Subtract 1 off each side. So that's going to get y squared minus 1 equals x. Now we finally have the function of y. So we write y squared minus 1 as that point. So that's kind of the, maybe that's not a drawback, but there's pros and cons to every method that you use. You just have to kind of be careful. Make sure everything's in terms of the right function. So now, we don't even have to worry about integrating. We can use our TI to plug these in. So let's see. Go back. Go back. And add this integral in, just so that we can see if we're getting the same answers. So again, math menu, 0 to 1, limits of integration, okay. So now we're going to, let's see, we can try it this way. If we're gonna use y, we can. You could also temporarily pretend it's x, as long as you're taking it with the same integral. Let's see. I gotta find the y key again. They're usually really close to the bottom. So, I mean, it's not a set variable, but if you were really specific, you can do, not second, you can do alpha 1, and that's gonna get the y, but I don't wanna be specific. I can. Let's see if it works. If not, we'll go back to the drawing board. I don't want caps though. So let's see. Do this one more time. We want square root first. And if you want to get the y, we're just going to go alpha 1. Well, let's see, minus. Okay, now we're saying y squared minus 1. So again, alpha 1 with a square. Subtract off 1. Now remember, you're subtracting off that entire expression, so you have to include the parentheses. But now we have to make sure we are taking it with respect to y. Let's see if it gives us something. I'm curious. Some older calculators won't, so. Ah, it did. But had you wanted to just write it in x because it ends up being faster when you type it in, no problem. But notice, no matter how you slice it, you ended up with the same area. Let's record this one more time. There we go. Notice with our TI, we got again 1.3333 square units. So this was a sample of doesn't really matter how you slice it, as long as you're doing this correctly, you're getting the same area either way. So these are a few problems that you'll come into as far as when you're practicing some of the techniques. Hope I've covered all of the troubles you may run into, and hopefully you can address it when you run into this. I would just kind of give you a heads up for 5.2 and 5.3. It's probably helpful to have everything printed out, because it's easier as we add diagrams along the way, so that you don't have to keep drawing original pictures. That would be my advice. But that's just a heads up for the next section. I will see you then.